So we're recording, we had the prayer, we had announcements and so on, and now we're just getting into the heart of the matter, as it were. I had a number of students who couldn't make it tonight who asked for a recording, so I don't usually do that, but tonight I'm doing it. So watch your language. Okay. Yeah, I want to go over a couple of the terms in the list. And then on page 2 of the agenda, we got partner with a or problems. I forgot what PWAP stands for. Practice with a partner. Duh. Practice with a partner. And it's the free response thing. Just, it's a very simple proportion confidence interval problem. It is from the College Board, so it's worth making sure that we're clear on it. And again, the number crunching is a part of these problems, but it's not by any means the central part. Okay, kind of the thinking and being able to explain why you're doing what you're doing and the rationale, I think, is really critical. So we'll make sure that you're comfortable with that. Okay, so let's get into it. I hope that sounds like a good plan. Make sure you pose questions along the way, but let me take a look at my agenda and just go through. There are 1, 2, 3, 4, 5, 6 that I want to hit and make sure that we're good. 2, 3, 7, 8, 10, and 14. You don't have to write that down, but let's take 2 and 3. The meaning and purpose of confidence interval for estimating a proportion. And then 3, justifying a claim about a population proportion based on a confidence interval. All right, so let's head over there. I'm just looking at my notes here. Here we go. All right. Well, just kind of a 30,000-foot view here. Hypothesis testing is all about, I don't want to say educated guesses about data, but I'm going to say it. Making some educated guesses about what data seems to be indicating. Notice I was qualified in the use of my language here. That's typical of statistical lingo in reporting results. We have these inferential techniques that we're going to talk about tonight and the next unit and the unit after that. And inference, as you know, means looking at some data, some evidence, and then drawing a conclusion. Now, the reason that we use not emphatic, well, this proves, it indicates, let me just get Andre. Sorry about that. Okay, the language of inference doesn't prove very often. It can point to in a kind of a nuanced way. So you want to be subtle in reporting what you find. You want to say the evidence seems to indicate, or based on our inferential techniques, the evidence seems to refute the null hypothesis and support the alternative. You always want to hold the door open for doubt, because there are things called p-values and the alpha level, which we'll talk about, and the probability of making an error. They call it in the language of probability type 1 and type 2 errors. And we'll talk more about that when we get into hypothesis testing. But one of the things I want to say about confidence intervals is if you don't know, let's say the proportion of registered voters in a district that you want to find out who they're supporting, let's say in the presidential election. So you take a poll, you have people, hopefully a lot of people, answer a couple of questions and so on, and then you make some inferences based on the results of that poll. So we don't know how many people support Trump, how many people support whoever the Democratic nominee is, for example, in the presidential election. We don't know, so we have to do polling and make some inferences, some educated guesses. But again, it's not certain. You know, certainty is not in the picture. But some data that indicates possible outcomes is what we're talking about. So a confidence interval always tells us more than a hypothesis test about a proportion. You may have run across, let's say, a hypothesis test for what's the proportion of college freshmen who binge drink. Okay, they get get a little freedom and then they go crazy and get drunk frequently and severely. What's the proportion of binge drinking on American campuses? That might be a possible research project where people pollsters would collect data based on interviews and so on. And then the whole question about are the wording of the questions going to skew the results? Are people being honest on a survey like that if it's anonymous? And there's always the chance that chance explains the results that we get, just the random chance of the people that we happen to include in our sample. It may or may not match up with the true population proportion. So that's another thing I want to say. What inference procedures are all about is trying to make a statement about the nature of something that we can't really know, which is there is, we could talk philosophically, there exists the true proportion of college binge drinkers on all American campuses, right? But we don't know it. Therefore, that's why statistical analysis and polling and research and so on comes in. All right. So let's see. Yeah, I want to do. All we can say about rejecting or failing to reject a hypothesis in a proportion is that, if it says the null hypothesis is equal to 50%, the alternative hypothesis is that it's greater than 50% or not equal to 50%. Once we crunch those numbers and come up with a statement, all we can say is the evidence does not support the null, that it's 50%. Okay, that's all we know. That's why I like confidence intervals, because what a confidence interval tries to do is to, given conditions, and we'll talk about those conditions in a minute, if the conditions are met, we've got a method that will capture the true population proportion value 9 out of 10 times if it's a 90% confidence interval, or 95 out of 100 times, okay? Again, if, and this is a big if those conditions are met, and we'll talk about the 3 or 4 conditions in a minute. But that tells us more, right? That gives us a range within which are plausible estimates of the true population proportion, which we'll never know. Binge drinkers, what's the proportion? We don't know. We can agree maybe philosophically that something like that does exist. Living in a college town, I can tell you it does exist. But to make definitive numeric statements about it, we have to use the estimation techniques that we're going to talk about. All right. So let's talk about a little bit about hypothesis testing, and then we'll come back to confidence intervals. All right. So another observation about confidence intervals, we should use a confidence interval to estimate the population parameter, okay? And then we use a significance test to assess the evidence of a claim about that parameter. I like that. Let me just say that once again. We use a confidence interval to estimate the population parameter. Binge drinking, Trump supporters, Democratic supporters, whatever the parameter of interest is. And we use sample data to do that. But we use significance tests to assess the evidence of a claim about the population parameter, okay? So we don't know what binge drinking is. We go out, ask some questions, do a poll, and then crunch the numbers and come up with a statement, a range of plausible values. And then, so a hypothesis test or a significance test takes one value and doesn't concern itself so much with a range, but one value, and measures that claim that that's the true population parameter, and sees what the evidence, whether it supports it or not. All right. Okay. Stating hypotheses is a very important part. The null hypothesis is H sub O, as you know, and that's the claim of no difference. Nothing's going on here, and it's the claim that we're weighing evidence against in a statistical test. Okay. The alternative hypothesis, H sub A, is the claim about the population that we're trying to find evidence for. And then I'm just gonna take some, or show some notes here. Oops, let me share my screen. What was the kanji of the day? That's kin or kon, which means gold. In Japanese anyway, I don't know about Chinese. Okay. So just so we're sure, that's how we write the null hypothesis, let's say, and we're saying that the population, or the population proportion, it's always stated in terms of parameters, not sample data, equals 80%, okay? Let's just say, I don't know, I'm making this up here. And the alternative hypothesis could be stated in a number of different ways. Let's say it could be stated that, no, the alternative hypothesis is that the true population parameter is greater than 80%. Or, and that's called a one-tailed test. Or we could do a does not equal and say that that's a two-tailed test. The alternative hypothesis says, no, that the population parameter or the population proportion is not equal to 80%. Okay, doesn't claim very much. All right, so this is a two-sided test. Whenever you see a does not equal, that's a two-sided, which means, I'll just draw a little sketch here. We don't know, let's say the null hypothesis is that the true population proportion is 80. And if we say, let's say it's 56, okay? Let's say that's the true proportion, all right? And the data supports that. So the alternative is that it's not equal to 80. It could be, we don't care, or we don't know. It could be 56%, it could be 99%. But all that we're saying in this two-sided test is that it's not 80%, all right? The proportion is not centered at 80%, it's centered at 99% or centered at 56%, okay? All right. Stop for a second. Assumptions. Let's talk about assumptions. There we go. Okay, conditions for estimating a proportion. First of all, the sample data has to be random. The data has to come from a well-designed random sample or randomized experiment. So the randomization of data, that's a big condition. If we're going to use the normal approximation for what is in essence kind of a binomial, you may remember the binomial distributions, success or failure and so on. If our counts are large enough, we can use a normal approximation for the binomial distribution. Now that's going way back to 2019. But large counts, both n times p and n times q, or let me share here and we'll just write that out. So assumptions. First of all, random. The data needs to be randomized or from a random experiment. And this is for estimating P, the population proportion. The second assumption is large counts. And this needs to be, n times P has to be greater than 10. And n times Q, which equals n times 1 minus P, has to be greater than 10 also. So n times P has to be greater than 10, and n times Q, and Q is defined as 1 minus P. It has to be greater than 10. So that's large counts. That enables us to do the normal approximation of the binomial success failure thing. And then we need the 10% condition. If we're talking about sampling without replacement, we need to have, let's see, 10% condition. Our sample size needs to be less than 1/10 of our population. Okay, so lowercase n stand. Yes?
Do you mind sharing your screen so I can see your calculations?
Oh, very bad. Me. Okay. All right, there we go.
Thank you.
Okay. Thank you for telling me. Yeah, so these are the assumptions for estimating a proportion. First one, the data must be randomized. Second one, we have to have large counts. And why do we have to have large counts? So that we can use the normal approximation. What's the normal approximation? That's that lovely standard normal distribution, which is bell-shaped, symmetric, unimodal, and all those good things. We know a lot about that distribution. So large counts, what does large counts mean? N times P hat has to be greater than 10, and N times Q, and Q is alternative notation for N times 1 minus P. It has to be greater than 10 as well. So both N times P and N times Q need to be greater than 10. And then the last condition is they call it the 10% condition. If we're sampling without replacement, we take a poll and we get 150 people, 150 registered voters. We don't take one, interview him or her, put them back in the population, then, select again. So we get our sample 150, and we don't put them back in the population. We interview them, and it's one and done. So it's called sampling without replacement. And in order to make sure that it's conforming to the normal approximation, we have to have our sample less than 1/10 of the population. So those three conditions are very important to know in conducting a hypothesis test and in constructing confidence intervals, okay? So let's just talk about this for a second. When the large counts assumption is violated, the capture rate is usually lower than our confidence interval. Let me say that one more time. If we don't meet that large counts thing, where n times p and n times q are both greater than 10, if we want to construct a 95% confidence interval, for example, chances are good that that will not occur. Right? So if we state that we're going to construct a 95% confidence interval, we've got to make sure that that large counts is met. If we don't have random data, there's very little point in constructing a confidence interval, for example, because it severely hampers our ability to make generalizations about that data. And if we violate the 10% condition, the spread, the capture rate, will be greater than the reported confidence interval. All right, so again, all of these conditions need to be met. If one of them is not met, I would raise concern, okay? I'm not saying you should not go ahead and conduct the hypothesis test or construct the interval or both, but it is worth being very concerned and expressing that concern in writing in a problem, for example, okay? Okay. Let's go to a problem here, and I think that's going to help. Okay. Let's see, catching up to the chat here. All right. Let's go to the problem, and we'll come back a little bit. So the problem was a free response. It's on page 2 in the agenda. I'll read it here at first, step 6.5. It says a recent survey collected information on television viewing habits from a random sample of 1,000 people in the United States. Of those sampled, 37% indicated that their favorite sport to watch on television was American football. If I had been in this sample after the Packers lost to the 49ers, I would have said, no, it is not my favorite sport to watch. Anyway, so we got a random sample. Boom, one of our 3 assumptions is ticked off right now. It's a random sample of 1,000 people, so we're good there. 37% indicated that their favorite sport to watch on television was football. All right, so, and then 2 steps that they want us to do, and we'll do this together. A, construct and interpret a 95% confidence interval for the population of all people in the United States who would indicate that their favorite sport to watch on television is American football. All right, let's do that. So let's make sure we understand what the question is asking. This is a little pedestrian. I'm going slow because I want to make sure that we're all understanding it. So I apologize if you know this and you're eye rolling and so on, but I just want to make sure that we're all moving to the ultimate comprehension goal. So they're asking us to construct and then interpret a confidence interval. And why would they want us to do that? We want to use that evidence from that poll to make an educated statement about the nature of the American population viewing habits and what they prefer to watch, okay? That's a tall order. We only have 1,000 people, and we're going to make a statement at the end of this, a generalization that we are confident applies to a nation of 330 or 320 million people based on 1,000 interviews. You know, but because of our familiarity with the rules of probability and so on, and the sampling distribution of the sample mean, another very important concept from last semester, we can say with some confidence that we've got it. All right. So let's go ahead and build that confidence interval. I'm going to share first and ask questions later. All right, here we go. Okay, so a confidence interval, it says 95% confidence interval. So I'm just, if you, with your permission, I'm going to say CI for confidence interval. And then I'm just going to put a 0.95 to remind myself that it's a 95% confidence interval. And get rid of this. Am I sharing? Yes, I am. Is equal to a point estimate, and then plus or minus a critical value. We'll talk about that in a minute. Times the standard error of p hat. I believe that's right. So this plus or minus is sometimes called the margin of error. And you've heard that a lot in polling. 46% those interviewed think that Trump should be removed from office with a margin of error of plus or minus 3. Okay, so that's what the margin of error is. Cool. So a margin of error consists of a confidence interval and the standard error. So let's figure that out. Well, we already know the p hat, that was 37, right? So we can plug that in, plus or minus. Now it's a 95% confidence interval. All right, we'll talk about confidence interval, but that's associated with a critical value of 1.96. How do I know that? You just do. The 90% confidence interval is associated with a critical value of 1.64, and a 99% confidence interval is associated with 2.58, I believe. Okay, so these numbers are called critical values. Okay, because remember, we're making some inferences based on a normal approximation. So those are z-scores. And in this case, they're very special. They're called critical values. And they set up the parameter of what we're talking about. Now, one last thing we need, so that's what critical value is. And then we want to multiply that times the standard error. Just back up here. And yeah, the standard error of p hat. And let me just create some room here. I got to move things around, sorry. Just get rid of this. Let me just get rid of this for a second. So let's look at this close. The standard error, when we don't know the problem didn't give us the standard deviation. So we're going to estimate it from data. And then we call that the standard error of p hat. And that's equal to the square root of p hat times 1 minus p hat over n, the sample size. Okay? So I think we're all ready. Any questions so far? This is we'll plug in now the numbers here, but I wanted to do it by hand, and then we'll do it by calculator so you can see how cool calculators are. But no questions? All right, cool. So let's go ahead. And then we're going to play with it. You know, we're going to say, because they're telling us construct on 95%. Well, how about constructing an 88% confidence interval? We could talk about that, play with that. All right, so here we go. Our point estimate is 37%, plus or minus. We got that 1.96 is the critical value. And now we got to figure out what the standard error is. Well, let's figure that out here. It's the standard error was equal to 0.37 times, what is that? 0.63 divided by 1,000. All right, so that's going to be a small number. Let me figure that out here on my calculator. 0.37 times 0.63. I hope that's right. Mental math is not my forte. I get 0.2331 divided by 1,000 equals a tiny number, 2.3 with the e -4, so it's way over there to the left. And then a second function answer, I square root, second function square root, and then second function answer. And I get 0.01526, all right? So that's my standard error, or the estimate based on sample data of the standard deviation in this case, or the average distance from the mean, or the proportion. That was 0.01526. I think that's plenty. All right, so we should be, so that goes up in here. Let's just put that in there. 0.01526. You guys are already ahead of me. You know what the answer is, but I want to find out. I'm hoping this helps. 0.37 plus or minus, okay, times 1.9, oops, 1.96, 0.0299. All right, that's far enough. 4 digits is enough. So I'm done. I've got the point estimate of 37% plus or minus about 3%. All right, so what is that? So 0.37 minus the answer that I just did would be 0.3400, comma, and then 0.37 plus 0.0299 is 0.3999. Boom. And, you know, 4 decimal places, and I'm good. All right, so this is one way of stating a confidence interval, 37% plus or minus about 3%. And this is also a legitimate, I like that way because it states the range specifically, but either one is acceptable. And the bottom one says, we're 95% confident that the true population proportion of American citizens who prefer football, you know, to any other sport watching on television, is between 34 and about 40%. Okay. See what's cool and elegant about confidence intervals is we used data. Did we check the conditions? I don't think we checked the conditions. Shame on me. Well, let's retroactively check the conditions and see if this is a reliable confidence interval or not. We already know about, I thought we did, but you know, because I remember I saw randomized data. It's randomized, and how about large counts, n times p and n times q? Well, n times p, n 1,000 times p 37, that's 370. That's bigger than 10, so check. And the n time, or let's see, q 0.63 times 1,000 is 630. Check. So we got the large counts. How about well, 1,000, our sample size of 1,000 is much less than the American population, adult population, let's say, of 200 million people. So we're good there. So retroactively, we checked the assumptions. We should have done that, first, but we did it last. But we're good to go. So our conditions are met. It's legitimate to use a normal approximation in this case to construct a 95% confidence interval. Now let's go over to the calculator and just show you how easy it is to do what I just did with all that calculating by hand. All right, so here we go. We go to the stat menu, scroll over to tests. Let me just stop sharing for a second and just see if we're okay. Is this helpful? It was a spot check. Truthfully.
Yes.
Okay, good. Good. All right. Oh, okay. All right, back to it then. Share screen. So we're going to look for the correct menu item. So let me just do this again here. So you go to the stat menu, scroll over to tests, and let's see. We don't want 3 through 6 because those are hypothesis tests. We don't want a z-interval. We don't want a t-interval. We don't want 2 samples. That looks, A looks promising. 1 proportion z-interval. Let's see what that is. Okay, so we've got 3, I was playing with this before. We've got 37% of 1,000, which is 370. We don't have a 99% confident, we have a 95 because that's what they asked for. And now we're going to calculate. And there it is. See how fast it was? So there's our confidence interval. So we say this, and I want to make a statement about statements, statistical statements. We're 95% confident that the true population proportion of Americans who prefer football viewing, it lies between 34 and about 40%. Okay, boom, finished. Now let me go over here, and I'm just going to go up. In our course site, I put these up long ago, and now they're going to be these 2 things. Which reference procedure to use? We'll come back to that in a minute. But this is the one I wanted to show you. The top 10 useful phrases for AP Stats. Let's go there. And then scroll down to the bottom. So I highly recommend that you print this out if you haven't already, and really kind of commit it almost to memory. Phrases 6 and 7 are kind of relevant for what we're talking about. They say, I am confident. I am 95% confident. Let's say, I said we are, whatever. I am 95% confident that the true proportion in context of American viewers is between 34 and 40%. Boom. If you say that language, by the way, I got this at the AP Stats Summer Institute. Darren Starnes, he was a former chief of the testing questions committee. So that's the language, guys, to use, that lingo. Here's another way of saying it. So they got the word or there. I am 95% confident that the interval from 34 to 40% captures the true population proportion, and then in context of American viewers of sports. Okay. All right. So I just wanted to point that out to you. That's a course resource that we have, and there are others, and we'll go over all 10 of these, but they're really good. They're really, really good. Now let's just take a look at what the confidence level is. In the random sampling, if the random sampling were repeated many times, about 95% of the resulting confidence intervals would contain the true proportion in context of viewers. Okay, the confidence level, remember the question dictated the confidence level, 95%. Construct a 95%. So what is confidence level? Well, it's referring to the fall semester's examination of the sampling distribution of the sample means, in this case, sample proportion. If this was done a million times and we plotted that, remember central limit theorem, your Christmas present, all that good stuff. If that procedure was done, in other words, 1,000 people were interviewed, boom, throw that back in, another 1,000 out, do that 1,000 times or 10,000 times or 1,000,000 times. What would happen is it would capture the sampling distribution of the sample proportions would capture the true population proportion about 95 out of 100 times. Okay, so it would miss 5 out of 100. Pretty low. Okay, so that's what confidence interval is. And I said before that we were going to construct an 88% confidence interval, so I can talk about critical values and how to find them on the calculator. But that confidence interval, number 6, phrases 6 and 7 are really, really nice. I said we because I wanted to include you. So we are 95% confident that the true proportion of Americans who prefer to watch football is between 34 and 40%. Okay, now we could be wrong. Here at the beginning of the course, or beginning of the meeting, I said we could be wrong, right? I mean, there is a chance that we could be wrong, that we were just unlucky enough to pick the one sample out of 100, or one of the 5 out of 100 that doesn't capture the true proportion. But chances are good we're not 100% confident, but we're 95% confident, which is pretty good in this case. All right, good. That was fun. All right, now let me do what I said I was going to do, which is let's take that problem and mess with it. I realize we have to answer B. We haven't finished that yet. But I just want to mess with it a little bit and show you something cool about the calculator. So let's share screen. Again, go over here. And let's say, we want to construct an 88% confidence interval. Oops. I just made that up. We could make a 60% confidence interval. But let's do 80 confidence interval. 88. All right, of the same data. So let me just draw a kind of a diagram here. So what we're saying is we want some critical values, right? In the 95% confidence interval, the critical values relevant were 1.96 above or below. And so the critical values are going to change. Obviously, it's not going to stay negative 1.96. So how do we find that out? If we're doing an 88% confidence interval, what we do is we center that in a normal distribution, the standard normal, and we got to figure out somehow what the critical value is in order to finish constructing that, right? Because plus or minus, we want the critical value and then the estimate of the standard error. Okay, we already know this. So what's this for an 88% confidence interval? Good question. Let's use the calculator to find that out because I have no idea. All right. Get rid of all this. And so what we do is we go to distribution, so second function vars, and there's that inverse normal. All right, that'll kick out a critical value. or let's see, so 3, that's what we want. And, oh, what's the area? Let me go back here. Well, 88 is 12 short of 100%. So in each tail, it's got that tail probability under the normal curve would be 6%. 6% plus 6% is 12% plus 80%. Then we got the whole thing. All right, back to the calculator. So area is 0.06. Mu is 0 because we're talking about the standard. And then the tail left. Okay, left, yeah. And then go down. And there's the critical value on the left side. Okay, we could have asked the calculator to do the right side, but so it's negative 1.555. Okay, so let's go back to our sketch. So now we know that the critical value on the left side is negative 1.555, and on the right side is positive 1.555. Okay, so that brackets the 88%. Now, let's just finish this 88% confidence interval. So, so the confidence interval is 0.37, critical value of 1.555, and what was this up here? 0.01526. All right, so calculator, please. So let's see, 1.555 times 0.01526. Turn the thing on, SLR, jeepers. 1.555 times 0.01526 times 0.37 equals, all right. Oh, whoops. 0.37 plus or minus that value. So do it again. 1.555 times 0.01526. 0.37 plus or minus 0.02373. All right. Now we so that's 0.37 minus answer. So the lower bound is 0.346. The upper bound is 0.37 plus 0.02373. 0.3937. Okay. A little bit narrower. All right. Now our confidence went down from 95 to 88%, but look what happened to our interval. It expanded a little from 34. It got smaller or narrower interval. It was 34 to 40, and now it's 34 and a half, and to a little less than 39 and a half. Okay, so we lost some confidence. I am 88% confident that blah 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 blah, in context and all that stuff, and but our confidence interval itself, the values kind of got a little bit more squished. So we're getting closer to the population parameter, but we lose something in the confidence level. I hope that was instructive. And then let's go to part B, and then that should finish us up. All right, I'm going over time a little bit. All right, so let's just see if we did everything right. Construct and interpret a 95% confidence interval for the proportion of all people, blah, blah, blah. We did that. And we're going to interpret it, right? We said we are, or I am 95% confident, blah, blah, blah. Okay. B, based on your answer to A, is it reasonable to believe that 33% is the actual percent of people in the US whose favorite sport to watch on television is American football? Justify your answer. That's a piece of cake, guys. We can say no, right? I mean, I would say no. Why? Because that 95% confidence interval, the lower bound was 34%. That's the lower bound. All right. And so they're giving us a 33. That's outside our confidence interval. So that is not a reasonable, right? When we constructed a confidence interval, we were talking about identifying, using this fancy method, plausible values of the population proportion. And we did that. We were strict about it. We checked assumptions eventually. We checked assumptions and so on, and found that the interval was between 34 and 40% roughly. So anything outside that, 41%, 42%, no, that is not a reasonable to believe. Why? Because we constructed a confidence interval of plausible values for the population proportion, and that is not in our interval. Okay, make sense? Let me make sure that I got everything. Yeah, I think so. All right. Okay, good. Questions, comments, criticisms? Any? Let's see. Yeah. I guess I'm trying to think if they're looking for something more than just saying, no, it's not a reasonable estimate of the population parameter in this case because it's outside our calculated interval of plausible values. That's what I would say. I guess one period, one sentence. All right, guys, let me stop recording.
No, I have. Can I?
Okay, go ahead,
share
Diego.
something? So I noticed that the question was actually the step 6.5.
Yes.
Can I share my answer to part B and you can tell me if it's correct?
Please do.
So I wrote that on part B that based on my previous answer, that assumption is invalid because 33% is not included in the 95% confidence interval. Furthermore, the actual percentage of people in the United States whose favorite sport on television is American football is impossible to calculate. Even if you survey the entire United States, you can be sure your survey wasn't affected by some type of bias or error.
I would leave that last part off. I think I know what you mean, but I think the grader would get miffed, to be honest with you. And
Okay.
by miffed, I mean irritated or annoyed, because it's kind of over explaining.
Okay, yes, understood.
Okay, and it's part of the gamesmanship of test-wise skills. I know what you mean, and I agree with you. What you said was true, but not necessary in the context of this problem. But the first part of can you just read that one more time, the first part?
Yeah, so the first part was that based on my previous answer, that assumption is invalid because 33% is not included in the 95% confidence interval.
Okay, period. Okay, full stop. And
Okay.
one other suggestion to improve your answer is replace the word invalid with not reasonable, right? Because I think they say, is it reasonable? Validity and unvalidity are very precise terms naturally in statistics. So validity, reliability, they're all measures for that. So I would stay away from validity and go with no, it is not reasonable, or it's unreasonable because it's outside the value of plausible values that we calculated, or that I calculated. You.
Yes, okay, perfect. Thank you.
Makes sense? Okay, good. Great, thank you. Any other questions, comments, criticisms? All right, guys. The kanji for today is jo, or sho, which means upper part. Cool, and I'll draw it for you, and then I'll let you go. Here we go. Stroke order matters. Boom. Joe. Show. And it means upper part. Cool. I'm in first grade. If I were in Japan, I would be in first grade, learning the first 80 kanji. All right, you guys. Have a good rest of the week. Is it test this week? I think it is.
Yeah, I think it's Friday.
Okay, well, good luck. Let me know if you have any questions or concerns before the test, not after. Okay, good. Oh, Tiffany, thank you. That also means up in Chinese. Awesome. We're communicating. All right. Take care, guys. Bye.